computer yet. Okay, so let's do a little recap, just a basic recap. We talked about QPI. First of all, we talked about system buses and the different types of buses. And then we saw that the bus was not really, it couldn't keep up with the higher and higher data demand by the devices that we have. So they introduced the point-to-point interconnect, and it was supposed to solve the issues that we had with the buses. So one of the point-to-point interconnect is called the QPI, Quick Path Interconnect. We already talked about this one. It has multiple layer protocol architecture. It uses packetized data transfer in comparison to the bus, which transmitted streams of bits, raw bits. For this guy, I mean the QPI, it was more organized. They had the protocol layer and all those layers. And the data transfer was in the form of packets. And you saw that these packets were in fits, in flits, and the biggest unit of transfer was packet. Packet is comprises of many flits. Now flits is 20 bits of data, flits is 80, and packets is a lot of flits. So for the QPI layer, we have seen that it has 4 layers altogether. The physical one, we know that it has all these wires. And then we talked about what was link. And then we talked about the routing layer. The routing layer tells us what are the paths that the packets can travel to and which is the best path to go to. And then we have the protocol layer. So this was our physical layer. And we talked about how the QPI uses the multi-lane distribution using simple round robin scheme. So what was the simple round robin scheme? It's basically you have a stream of data. In this case, this is a stream of flits, and it organizes from here 1 to, oh, why is it not working? Now 1, no, wait. Draw. Okay, so first you go over, why is it not working? So I'm being sabotaged. Come on, I already fixed this just now. Okay, let me see what's going on. Okay, please send your prayers to my pen. Still not working. Your prayer is not good enough. Please pray some more. Okay, so your flit, why is it not working over here? Should I give up on this? Okay, let me try one more time. I want to redo this. Let me pause the recording. How do I pause this? More. Resume. Okay. Oops. Too far. Okay. Continuing. Let's see if this pen is not working again. Okay, I just need to relax when I use this pen. It realizes it can detect my fear. Okay, so we talked about the physical interface. This is how it looks like. And then we talked about the lanes. If you still remember, the lane has 2 wires, and whatever that I told you, please try to remember it. It's all over here. And then we have the multi-lane distribution, and I told you it uses the simple round robin scheme. It's okay. I'm going to give up on this slide. So it goes from here and here and here, and then goes up again to QPI lane number 0, and then QPI lane number 1, then 2, 3, 4, 5, up until whatever number of lanes that it has, back to number 0, based on this stream of flits. It's like you are in a queue, and this is me going over here, and then this is me, and then me as in MIE, and then we have, who else? Haziq, and then we have Henry, and then who else? We have Colleen, and then we go back up here again with another person. So it depends on the queue, and this is the simple round robin scheme. So the QPI link layer, there are two functions, which is flow control and error control. So how does it do the error control? Please take a look on the explanation and make sure you are aware of how it does the error control. Okay, so it uses the CRC. And then we talked about the routing layer and also the protocol layer. The protocol layer basically checks if the cache is consistent among themselves and more. The unit of transfer is in packet. And then we talked about the PCI, but I told you PCI, there are a lot of types of PCI, but we are going to discuss about the PCI Express. This guy over here. The key requirement is high capacity. Okay, never mind about this one. And then we talked about this configuration. The chipset, we have a chipset that is connected to PCI links. And the chipset is also connected to memory and also to core. So the chipset acts as a buffering device to deal with different data rates between I/O controllers, memory, and core. So they all have different data rates. So the chipset helps to like it helps to like translate or like make sure. Oh yeah, it does translate. Translates between PCIe transaction formats and the processor and memory signal and control requirements. So basically it acts like a translator. So we have seen a device acting in a similar way, which was the I/O hub for the QPI configuration. So the QPI, in the QPI, the IOH or the I/O hub was translating between the PCI link to the I/O, if I'm not mistaken. It was translating the formats. So the chipset does a similar thing, but between the memory core and all these PCIe connected devices. So here we have the chipset also connected to a PCI Express link that is connected to a switch. So the switch is connected to other PCI Express links that is connected to a legacy endpoint, PCIe endpoint, and more PCIe endpoints. So the guys over here, or the devices connected over here, are like the slower ones, whereas the ones that are closer to the chipset require high data rates. Okay. And then for the PCIe, we can see that it has 3 layers in comparison to the QPI, which has 4. And we have seen that the unit of transfer for QPI was FIT, and packets, whereas for PCIe, we have a slightly different name called the data link layer packets, DLLP, and transaction layer packets, TLP. Now this name seems a little bit long, but remember that these are all layers. You only have to memorize, like, this guy has 3 layers: physical layer, data link layer, transaction layer. This already gives out the name: transaction layer packet, data link layer packet. So you just have to memorize these 3 and remember what is the unit of transfer, TLP and DLLP. And this is what it does in general. Don't know why it's disorganized today. And then the PCIe also uses the multi-lane distribution. We also talked about this one as well, except that for the PCIe, the distribution is in the form of bytes. So previously in the QPI, it was flits. This guy is in bytes. But for the PCI, a multi-lane distribution, compared to the QPI is only one direction, or you can say it's unidirectional. Once you send it out, there you go, you're not coming back. But for the PCIe, it acts like a parent. You have like the bidirectional thing going on. I send my son to a university. I expect my son to come back to my house. So it's a bidirectional thing. So this is the difference between PCIe, apart from the byte stream versus the flit. And also it is bidirectional compared to the QPI, which is unidirectional. Okay, so here each block of 1 to 8 bits is encoded into a unique 130-bit code word. So the data is 128, but it is mapped onto a 130-bit code word. We will discuss why. For transmission, this is referred to as 128 bits over 130-bit encoding. Now, encoding is a method for synchronization. Thus, the effective data rate of an individual lane is reduced by a factor of 1 to 8 over 130. So the effective data rate reduces because you are only transferring 1 to 8 bit, but you are using 130 to do that. So basically, you are not being very efficient, right? But there is a reason why they do this. So we will discuss this. So the rationale behind 1 to 8 bit over 130 bit encoding. Do I want to read this slide? Okay, so the PCIe does not use its clock line to synchronize the bit stream. Now, this is an important keyword to understand why we have the 128 over 130 bit encoding. So if we have a clock, we don't necessarily have to rely on anything except for the clock. We have different time slots, and if I want to transmit my data at time slot number 2, I can just do that. But here, they don't use clock except for control signals. So they don't use clock. So what they do is they look for transitions between the bit streams. They look for transitions between the bit streams for synchronization. So this is why, and let's talk more on that. Okay, so method of synchronization in PCIe. So there are two types. The first one is scrambling, and the second one is encoding. So encoding, we talked about encoding in 128 over 130 briefly. So what exactly are these two methods? So scrambling, I just put a scrambled egg here so that you are more interested in the slide. So scrambling, which does not increase the number of bits to be transmitted. Now, it does not change any data, unlike encoding. Encoding increases to 130. So scrambling does not increase the number of bits to be transmitted. Is a mapping technique that tends to make the data appear more random. Now, why do we want our data to appear more random? The scrambling tends to spread out the number of transitions so that they appear at the receiver more uniformly spaced, which is good for synchronization. So when you transmit data, sometimes it looks like it's not fluctuating. It's like a single line. So I'm at the receiver, I look at this data, it's a single line. What on earth is this? It looks like a ruler. So I don't know where the end, where does it start, where does it end? So to overcome this, they scramble this data so that it has some fluctuations. It's not exactly called fluctuation. You have the ups and downs. So when they see that we have the ups and downs, it is more, how do I say this? It is easier to see where the data starts and ends because it's not like a straight line. So this is what the scrambling does. It gives out these little transition points so that the receiver can look at it. Oh, okay, so we are still in sync because, let me try to draw this. I can't draw this. I am so sorry. Let's try again. Okay, so instead of, let's say you are transmitting a data line that looks like this, and then it's like there's a long gap between a drop in the signal, right? So at the receiver, I'm just waiting. Oh, it's still a straight line. I'm just waiting. Oh, it's still a straight line. So the receiver is like, it's just like us. It's like sleepy when it looks like when it looks at a straight line. So what the scrambler does is it has more dips in the data or more dips in the signal. So when you have more dips, when the receiver looks at it, it's like, oh, okay, I'm still in sync with this guy. And the next time it looks at it, oh, I'm still in sync because we have the same dips going on. So let's say that, oh, what happened? Excuse me, what are you doing? Honestly, this thing is sabotaging me. Okay, let me try again. Okay, it's not working. So I hope you can imagine that. So if you have like more dips placed more evenly spaced, the receiver can actually look at it and see, oh, okay, I'm still in sync. So this is what the scrambling does. It puts in more transitions in the data so that we know that we are in sync, the transmitter and the receiver. Okay, this is good for synchronization. So this is one technique to synchronize in the PCIe. So the second one is called encoding, which we have briefly talked about, the 128-bit over the 130-bit. Now, this technique increases the number of bits in which additional bits are inserted into the bit stream to force transition. So basically, you're putting in additional bits and you are forcing transition. So this forced transition induced by you or the encoder, it acts like a queue for the receiver. Okay, so this is the transition. Please wait for the incoming bit stream, the next incoming bit stream, because this is where it ends, for example. So this is what the encoding does. The additional bits tells the receiver, hey, keep a lookout. There's going to be a new bit stream coming. So for the PCIe, each group of 1 to 8 bits of input is mapped into a 130-bit block by adding a 2-bit block sync header. So you have that header to tell the receiver, hey, watch out. All right, so those are the two methods of synchronization. So these are two transmit and receive block diagrams. Here you have the transmit and here you have the receiver. So let's talk in more detail for the transmitter and the receiver. So for the transmitter, first you have 8 bits over here. It goes into the scrambler. You know what the scrambler does. It puts in transitions more evenly spaced out. And then it does not add any bits. So you still have 8 bits, right? So for the 1 to 8 bit over 130-bit encoding, it acts to get the 128, it acts like a buffer and waits for the 8 bits to come in until you get that 128 bits. So the scramble output is fed into the encoder, which buffers it waits 128 bits and then maps the 1 to 8-bit block onto or into a 130-bit block. So it waits until it gets to the 128, puts it into a 130 block. The additional 2 bits is the header or the forced transition as a queue for the receiver. And then the 130-bit block is converted from parallel to serial. And then now you see that it is now a thinner arrow, which means that it is a serial. So the data is now transmitted 1 bit at a time. And then it passes through the transmitter differential driver. This block then passes through a parallel transmitted 1 bit at a time using the differential signaling. So this guy signals to the receiver. Okay, so moving on to the receiver part. So we get our differential signal. We receive it in the differential receiver. And then we have a clock recovery circuit. I'm going to talk about this later. We have the data recovery circuit, and then we are still getting in 1 bits, right? So the 1 bit that we are getting in the form of a stream is now converted to parallel. So now the arrow is small. It is a fat arrow. So 1 bit becomes parallel to become 130-bit in parallel. And then the 130-bit is decoded to become the 130-bit block. And then after it is decoded, it is descrambled. Sorry, it is decoded to become the 128-bit, and then it is descrambled, and then it returns to its original form, which was the 8-bit data. And this guy shoots out 8-bit data until the data is done. Okay. Any questions about the transmitter and receiver? Everyone is okay? Okay, I assume everyone is okay. So if you have any questions but you are too shy, you can also type it in the chat box. So here is something to note. Each transmission of a block of data over the PCI, I'm recording, right? Okay, yes. So each transmission of a block of data over a PCI link begins and ends with an 8-bit framing sequence. With an 8-bit framing sequence to give the receiver time to synchronize with the incoming physical layer bit stream.
Doctor, can you show me the previous slide?
Okay, sure. Any questions about this one?
Just hold up. I'm trying to read. Oh, okay, makes sense. Nothing. It's okay.
Okay. Okay, so let me just explain this again. So first we scramble, right? And then we encode, and then we change it to parallel, from parallel to serial, and then we transmit it using the differential driver. So basically whatever that is done to the data, we need to return it back in the receiver. So here we have parallel serial, encoder, scrambler. Parallel serial to parallel, decoder, descrambler. So we have these 3 steps in reverse order because this is what we've done to the data. So we have to reverse it. So in this sense, I wanted to talk about the clock recovery circuit and data recovery circuit. What did I want to talk about? I don't think we should put too much emphasis on this. Wait, let me try to remember. Receiver. Okay, so here I told you that we need to take note that each transmission of block of data over a PCI link begins and ends with an 8-bit framing sequence. So you started off with 8-bit, right? This is your 8-bit sequence. And when you end, you also end with 8-bit sequence. So this 8-bit sequence is intended to give the receiver time to synchronize with the incoming physical layer bit stream. So that is just it. So it just wants you to take note that we start with 8-bit framing sequence, you end with 8-bit framing sequence. Okay, so I think that is it for the PCI receive and transmit block diagrams. If you have any questions, you can ask me. So we are going to talk about the transaction layer, which is the most top layer in the PCI layer. So the transaction layer receives read and write requests from the software above the TL. So we have all our layers, and above our TL is our software. So it receives read and request from the software above the TL and creates request packets for transmission to a destination via the link layer. So the transaction layer, we have the transaction layer, and then down there we have the link, and then down the link we have the physical. So the TL creates request packet for transmission to a destination via the link layer. So most transactions use a split transaction technique. What is that? And then some transactions are posted transaction. What is that? We are going to talk about that. And then the TL packet format supports 32-bit and also extended 64-bit memory addressing. So the transaction layer can go from 32 up to 64. So what is split transaction technique? So split transaction technique is a request packet is sent out by a source PCI device, depends on what the source is, which then waits for a response called the completion packet. So this is the unique thing about the split transaction technique. It sends a request and then it waits for the completion packet. But while it is waiting for the completion packet to come back, the PCIe can do something else. So this is why it is fast. So the completion following a request is initiated by the completer only when it has the data and or status ready for delivery. So it only sends out the completion request or the completion to the request only when it is confident that it is ready. So each packet has a unique identifier that enables completion packets to be directed to the correct originator. So even though the completion of the request comes in later, it is not a problem because you won't be mixing up the addresses because they have the unique identifier. So with the split transaction technique, the completion is separated in time from the request. So this is why the PCIe is fast, because while waiting for the request to be done, they can do something else. It doesn't have to wait. So this is in comparison to a typical bus operation in which both sides of a transaction must be available. So if I'm calling out to, let's say I'm calling out to Colleen. So Colleen has to be on alert at all times. Colleen is going to be very anxious because she knows that I can call her anytime and I don't want her to be delayed in responding to me. So Colleen has to be on high alert. I have to be on high alert whenever we have this communication going on, versus the PCIe transaction layer. They can do something else. It's very much relaxed, but at the same time, this also makes it more efficient. Okay, so between the request and the completion, other PCIe traffic may use the link. Okay. So I told you that the TL packet supports 32 up to 64 bits. So these are the 4 address spaces that the TL supports: the memory, IO configuration, and also message. This is some examples of that. You can just go over it later. Not very important in my opinion. And then I want to talk about the PCIe protocol data unit format later, and TLP memory request format also later. So let's go over to chapter 4 first. So I'm going to save this. Oh, I'm supposed to save it. Never mind. So I'm going to close this. Does anyone have any questions about chapter 3, apart from the ones that I skipped, which are these two? Any questions? Okay, no questions?
No, Dr.
Okay, so let's go for another, okay, let's take a 5-minute break and come back at 4:40, and I'm going to continue another 20 minutes. Okay, so 5-minute break, come back at 4:40, take your drink, go to the toilet, whatever. I'm going to open my chapter 4 now. Okay, so I need to remember other people's name so I don't keep on calling Colleen. Okay, I'm gonna use Tashrin's name. Maybe Amina. Safwat, okay. My next 3 victims. Share screen, chapter 4. Let me reduce this one. Okay. Okay. Okay, so I hope everyone is back. Let's continue for another 15 minutes or so. Okay, so we are in chapter 4. We are going to discuss about cache memory. The pronunciation is cache. Oh, forgot this thing is not working. Okay, so for cache memory, it is part of the memory. And these are the key characteristics of computer memory system. Okay, sorry. So these are the key characteristics of computer memory system, whereby the cache is inside the internal memory. So we have internal memory, which is consists of the processor registers, cache, and also the main memory. So the main memory, we have seen that the main memory is next to the cache before, and the cache is next to the processor register. Or was that in this chapter? So yeah, I think we have seen this diagram before. And then for the external, this can be your hard disk, hard drive, and stuff like that. And then for the capacity, you can describe your memory in terms of number of words or number of bytes. And then the unit of transfer can be in the form of word and block. We'll see what that means. And then for the access method, how do you access the memory? We have several techniques. These are just the basic ones. There are more. As technology evolves, obviously. So we have the sequential, the direct, the random, and associative. And then we have, in terms of performance of the memory, we look at it in terms of the access time. How long does it take to, access the memory? And then cycle time and also the transfer rate. And in terms of physical type memory, we have the semiconductor, magnetic, optical, magneto-optical. I wouldn't focus much on this one. And then in terms of physical characteristics, volatile, non-volatile, I expect you to understand what this means. That's it. And then in terms of organization, we have memory modules, which we have talked about in chapter 3, I believe. Okay. So characteristics of memory systems before we dive into cache. Location refers to whether memory is internal or external. I don't think we should go over this one. We already did this in here. Yeah, I think it's the same thing. Okay, so this is the method of accessing units of data in the memory. So access method means the technique that is used to store and retrieve data, and it is identified by the dataset organization. So it means here that the names given to these methods of accessing data is basically based on its dataset organization, based on the dataset organization. So here for the sequential access, it involves a shared read-write mechanism, not too important, but the memory is organized into units called records, which is arranged sequentially. So here there is a hint over here. The data is called units of records, and the records are arranged sequentially, which is why we have the name sequential access. Arranged sequentially in the order in which they are and they entered. So access must be made in specific linear sequence. You can't skip turns, and access time is variable because you are basically waiting for turns. Sometimes it takes longer to access one part. Sometimes it's shorter to access another part, and therefore we cannot really predict. So access time is variable. So direct access, it also has a variable access time. Why? Because it also involves a shared read-write mechanism, and the individual blocks or records have a unique address based on physical location. However, direct access most of the time combines with sequential access. So you have the direct access, and then it uses sequential access to complete whatever the task that it is requesting for. So direct access typically combines with sequential access, and access time is also variable. So these two guys are very much related. And then you have random access. Each addressable location in memory has a unique physically wired addressing mechanism. The time to access a given location is independent of the sequence, unlike the sequential and direct. Independent of the sequence of prior access and is constant. So the time is constant for random access. So any location can be selected at random and directly addressed and accessed. So this is great because of the physically wired addressing mechanism. You basically can just go there immediately. So main memory and some cache systems are random access, very fast. Okay, so another technique of accessing units of data is called the associative. This is slightly different than the rest of the accessing methods. A word is retrieved based on a portion of its contents. So you have a data, only a portion is, you only recognize a portion of the data and you retrieve that based on the portion of the data that you see. So each location has its own addressing mechanism and retrieval time is constant, great, independent of location or prior access patterns. So whenever you have a constant time, please know that they are independent of other requests. So cache memories may employ associative access. Again, what is associative access? The CPU looks at a portion of the data, and if it recognizes the portion as what the CPU wants, the CPU says, okay, I see some similarity to the data that I want. So this is it. I'm going to take it at this address. So this is the associative. It looks by the portion of the data that it sees. Okay, moving on. So these are the 4 methods of accessing units of data. Excuse me. So the two most important characteristics of memory are the capacity and performance. Capacity meaning to say how large it is, and performance, how fast it is. So three performance parameters to quantify this is actually the access time, the memory cycle time, and also the transfer rate. So access time is also known as latency. I think I have mentioned the word latency before, but not in detail. And then memory cycle time and also transfer rate. I think we know what this means. So latency for random access memory, it is the time it takes to perform a read or write operation. For a non-random access memory, it is the time it takes to position the read-write mechanism at the desired location. So this is the difference between the two. So latency is basically the time it takes to perform the read or write operation, to execute the operation, right? And then we have the memory cycle time. What is important here? Additional time may be required for transition to die out on a signal line or to regenerate data if they are read distractively. Do I remember what this is? Okay, so I think this is the important point for memory cycle time. Access time plus any additional time required before second access can commence. So basically, the next cycle, how long does it take before the next cycle can commence? So that is your memory cycle time. So you have the time, which is latency, which is the time to execute the operation. And then you have some time for like synchronization to happen or like to check the error and stuff like that. And then the next cycle happens. So how long does that take? That is the memory cycle time. And then for the transfer rate, the rate at which data can be transferred into or out of a memory unit, straightforward. Okay, so latency, memory cycle time, and transfer rate. I think those are the important things that you need to remember, the gist of it. Okay, so this one don't have to know. I want you to know what is volatile versus non-volatile memory. So we've seen this word before in the history, which is in chapter 1. So volatile memory is the information decays naturally or is lost when the electrical power is switched off. So let's say, oh no, I don't have an analogy for this one. Yeah, let's just keep it at that. And then for non-volatile memory, once recorded, the information remains without deterioration until deliberately changed. So you have your, I have an example for this one. For example, you have your Blu-ray, right? Yeah. So your Blu-ray is hard-coded, not hard-coded. Basically, the data is there unless you write over it. So it remains there without deterioration until deliberately changed. That is an example. But of course, the Blu-ray CD is not part of the computer. So that is just how I want you to relate things. Okay. So you put the data inside there. It doesn't go anywhere unless you write over it or you purposely erase it. So that is non-volatile memory versus volatile memory. Once you shut down your computer, the memory is gone. Okay. And then this one, you don't have to know except for this part. For random access memory, the organization is a key design issue. Nah, okay, moving on. Okay, so the memory hierarchy is important here. So design constraints on a computer memory can be summed up by 3 questions. So these are the very important questions that designers of machines ask themselves every day before they design. How much, how fast, how expensive? Sorry, memory designer. How much, how fast, and how expensive are the memories going to be? So the faster the access time, the greater cost per bit. The greater the capacity, the larger you have it, the smaller cost per bit. And then the greater capacity, however, slowest the access time. So how big do you want it? And how fast do you want it? So these are the things that you need to balance out. So the way out of a memory dilemma, we have a dilemma here, is not to rely on a single memory component, but to have multiple versions of it. You can have a memory that is fast, very, very fast, and you can have a memory that is slow, but larger capacity, and you combine them. You combine them and use it accordingly. When you need a fast memory, you use the fast one. And for the slow one, you reduce the frequency of access. So let's talk more on that. What time is it? Oh, okay. So I'm gonna end our class here and continue tomorrow. We will be having our class online again because some of your classmates are sick and I don't want the rest of you to become sick as well. So get well soon. For those who are sick, I will be seeing you next week, hopefully physically. Until then, until tomorrow, take care and have a great rest of the day. Bye, guys. See you later.
Thank you, Doctor.
Thank you, Doctor.
Thank you.